So, okay, let me start. People will come and follow. So, am I visible and audible clearly? Yeah, okay. So, should I start right now? Yeah, okay. So, welcome to the first lecture for assignment solving for the course of Chemistry and Physics of Surfaces and Interfaces. Uh, Myself is Tanmay Khan from IIT Kanpur, and I'm doing this as a part of my PMRF deliverable. So in this series, I will mainly try to solve the assignment given by the NPTEL faculty and the fellows. So today I am going to discuss the assignment of the first week. Okay, somebody has joined. I think. Yeah. I need to open it for everything, everyone. I think. Yeah. I don't need to admit it every time somebody try to join. Yeah, is there not any option like people can directly join with the link, or should I admit every time somebody is joining? Let me see. Yeah, yeah, I get it. I'm trying to see that. Okay, I'll like admit everyone every time it feels like. So, as I said, in this series, I will basically solve the assignment given by the faculty. And for today's lecture, I am trying to discuss the 10 questions for the assignment of week 1, right? These questions are mainly from the first five lecture video. So let's go to the questions. I'll talk like each question and try to give some no, like some theory behind it if it is there, and then solve it. Okay. So let's go to the first question. So I think the screen is visible to both of you. Okay. Now, see, this is the question is which surface has herringbone pattern, right? This is herringbone pattern. This is a special kind of pattern. Like this picture actually represents the herringbone kind of pattern, and this is a famous example of surface reconstruction. So, what is surface reconstruction? So, what is surface reconstruction? We need to know. This is already discussed by the faculty. So, what is surface reconstruction? So, if you think about any surface, right? Any surface, let's say some kind of some atoms are there in the surface, but these atoms are having lesser coordination number than the bulk. If these are the bulk, let's say, and this is the surface. So, due to that, this surface is actually having higher surface energy, but nobody can want to maintain that higher energy. So it will try to minimize that. So the property of the hello, yeah. So property of the surface is at the surface the density of atom is very low. At the same time, the coordination number of the atoms present in the surface is also very low, and due to which it will have higher surface energy, and it will try to minimize that. And that process of minimizing that surface energy is called as reconstruction of surface reconstruction. So let's just think what it will what it will do as a result of construction. So let's say this is a surface atoms. So these are having actually higher energy because of the low coordination. So the immediate next layer will come closer to compensate that, and that is called surface relaxation. This is relaxation of bonds. First one. Second, it can do like it can like two atom can come closer so that it will have a better interaction, and that's how they can actually minimize energy somehow, and that is called rearrangement of atoms. And missing row of atoms is also a special case of rearrangement of atoms. How it happens? Let's say this is there is five atoms in the surface. Let's say, and these three are coming close, and it becoming like hello, hello, am I audible? Sorry, hello, hello, hello. Am I audible now? Okay, okay, okay. Yeah. Thank you, Jaydeep, for telling me. Let's go to the problem again. So what it can be like seen. So like let's say three atoms comes very close, and let's say there are much more atoms. Okay, and another three comes very close, and one atoms that was there now it is not there. It can go to the bulk. So there will be a missing row. This one. So that kind of reconstruction can also happen. So everything I am saying, relaxation of bonds, rearrangement of atoms, missing row, these are to minimize the surface energy. And this process is called surface reconstruction. Now, like AU111, yeah, yeah, I am telling like, yes, 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 I'm repeating, I'm repeating. You can hear me, right? Yes, yes, yes. I'm telling that's what is surface reconstruction. The surface reconstruction is at the surface due to lower coordination because any bulk atom will have much more coordination with the atoms, but at the surface, like surface means there is no atoms above it, right? So it will automatically have lesser coordination number, and due to which it will have higher surface energy. But the tendency of anything is to lowering the energy, right? So let me admit them first and then. You see, I'm not talking anything, I'm just admitting the people's. Yeah. So what I was telling that due to the lesser density and lesser coordination number, the surface will the atom will be reconstructed in a manner that the surface will have minimal of energy. Okay, the surface energy will be like lesser somehow, and that is called surface reconstruction. It can happen in three manner like relaxation of bonds. What I said, what is relaxation? So the immediate next layer of atom to the surface will come a little bit closer, and that's how it can minimize energy. And another thing is two atoms in the surface, two or three atoms, it can come closer. Like these two, let's say, these two can come closer. This is also a rearrangement of atoms. Now also, like three atoms may be coming closer, and one row is missing because and that missing row it can go to the bulk or whatever it is. So that's how our like reconstruction is nothing but minimizing the energy. So this is a very like the AU111 surface go reconstruction and make this kind of pattern, which is called herringbone pattern. So that is what the answer will be AU111. Right? What is a herringbone pattern is like that, and that is a result of that surface reconstruction. And you can find this answer in lecture number 5. Okay, professor actually nicely explained that, and that's what I tried again explaining. Okay, so this was the first question. Come to the next question. What is it? This is a Haber process for producing ammonia. Okay, that is N2 plus 3H2 to 2NH3. And the question is, Is it an example of homogeneous catalysis or heterogeneous catalysis or both or none of the above? So first we need to know what is homogeneous catalysis, what is heterogeneous catalysis. Catalysis can be divided into two parts, like one is homogeneous and another is heterogeneous, right? So homogeneous means if all the reactants, right? If all the reactant and the catalyst are in the same phase, right? In this case, everything is in the same phase. If that is the case, like all the reactants and also the catalyst are in the same phase. Let's say catalyst also a liquid, and you are reacting with two liquid A plus B, and the catalyst C, that is also liquid. So everything will be in the one phase if that liquids are miscible. So if that forms one phase, that time it is called homogeneous catalysis. And if it is like catalyst and the reactants are having different phase, let's say your reactants are liquid but the catalyst is solid. So that time it will be called heterogeneous catalysis. So in case of Haber process, it actually happens in the presence of iron oxide, which is a solid. So N2 is gas, H2 is also gas, and the ammonia that is producing, that is also gas. But the catalyst, that is actually solid, right? So if reactants are in gas phase and the catalyst in the solid phase, so that means there will be two different phase. So what it will be? It will obviously be heterogeneous catalysis, right? Is there any problem? Okay. Now let's come to the third question, right? This is like there are 14 Bravais lattice in three dimension. Okay, and this is very famous. Like in this case, they have asked about monoclinic lattice, but people can like ask about triclinic or orthodromic, whatever. You need to you need to remember these things. Okay, you can use some trick by you on your own, but you need to remember because these questions are very like famous, and usually it comes in every course, every exam, right? So there I have given all the type of seven type of lattices and 14 kind of Bravais lattice depending upon the position of the atoms. So just see that is monoclinic lattice. In case of monoclinic, what are the condition? Like in a three dimension, the lattice parameter will be three lattice parameter will be there that are A, B, C, and with the three lattice parameter there will be interfacial angle that is alpha, beta, and gamma, and depending upon the condition of A, B, C, and alpha, beta, gamma, these lattices are classified. So in case of monoclinic, the condition is A is not equals to B, not is equals C, beta is not equals 90 degree, and alpha gamma is 90 degree. So if you go by one the options, so obviously you will find that like in every like don't need even go to the angles. Just go by the ABC equations and see that this only the third option is only having A is not equals B and not equals C. So that means this will be your answer, right? So you need to remember this are the condition for the lattices, right? And this is very important, I'm telling you, because in like gate also sometimes or in like CSI also sometimes they directly ask that questions. Okay, so this is a very famous question. You have already like whoever are from MSc, they are these guys are already known that. So this is a packing density of a lattice. So they have asked about packing density of BCC lattice. So what is packing density? If I am writing this is packing density. So what is packing density? Packing density is nothing but let me admit them and then I continue. Packing density is the volume of atoms in the unit cell divided by volume of the unit cell. So what it physically means? It means how much volume of the unit cell is occupied by the atoms, right? So you just see this picture. There are atoms in the corner of the cube and in the center. That is basically BCC structure, but there is very much space. So how much space is occupied by the how much fraction of space is occupied by the atoms? That is what is called packing density. So yeah, how you can do that? So you need to know the number of atom present in the unit cell, right? You need to know the number. Hello. Yeah. So you need to know the number of atoms present in the unit cell, and then only you can know what is the total volume of atoms present in the unit cell, and then volume of the unit cell. Because volume of the unit cell is known. If this is the lattice parameter is A, obviously a cube volume will be A cube. Total volume. I'm talking about total volume, right? So in case of BCC, if you look at the structure, so if you just connect this is the diagonal of this cube, and this diagonal is formed by two corner atom and the atoms present in the center. So that means this diameter, that is r, and this is the total radius, that is 2r, and this is, sorry, this is the total diameter, that is 2r, this is the radius of atom r and r. So this diagonal of the cube, if a cube is having length of a, then the diameter of the cube will be root 3a, we all know from mathematics. And what it will be? That will be r plus 2r plus r, right? So that means 4r is equals root 3a. So that means I want to know the a is 4 by root 3r. So depending upon the arrangement, in this case this is for BCC arrangement, I have calculated the relation of a lattice parameter with the atomic radius, right? So let me admit them first. Yeah. So I have calculated the lattice parameter, right? Now let me calculate what are the number of atoms present in that unit cell, right? So this there are 8 atoms in the corner. Like in each corner there is one atom of this cube, right? So if you think about this in a 3D, so this atom, one atom, will be shared by 8 cube. How? Like there will be one cube like this. Obviously, one cube will be in front of you. One more cube will be in this direction. So in the plane there will be 4 cube. One is this. One will be just left to this, and one will be the just front of that left, and one will be front of this itself cube. So in the plane there will be 4 cube, and above the plane there will be more like four more cube. So each corner will be shared by 8 cube. So we are having total 8 corner atom, but each of one will be shared by share 1 by 8. I am talking about number of atoms. Plus, there is only one atom in the center which is not shared by any other cube than this unit cell. So we can get the contribution of like this, oh, totally. So what will be the number of atoms? 1 plus 1. That means there is two atoms present in the unit cell. So now it is very simple. Just do the mathematics. What is packing density? The two atoms into the volume. That means volume of a sphere is 4/3 pi r cube by volume of the cube, that is nothing but a cube. Now if we just change a with the relation of r, we have already got what we will get, 4 by root 3 r whole cube. That means RQ will cancel and we will get a number. If you calculate, it will come 0.68. That means 68% of the 68% volume of the total volume is being covered by the atoms, right? Like so, that means what will be the packing density of BCC? That is be 68%. Is there any problem? I think you have understood this, right? Yeah, yeah. So I'll also talk about the FCC like this. You already know. So what will be the packing density of FCC? I'll just try to give. like for your, like you can also do that. I'll also solve it here. So how FCC looks like, there will be 8 atoms in each corner, right? And also there will be like one atom in the middle of a face, right? In each face there will be a atom. So what will be the total number of atom we want if you want to calculate? What will be, what will be the total number of atom? Again 1 by 8 shared 8 atoms plus, then think about this atom. This atom will be shared by 2 cube because there will one more cube in just above the plane. So each of these atom in present in the face will be shared by 2, right? So half of, and how much, how many such atoms are there? One, 2, 3, 4, 5, 6, right? So total number of atom is coming as 4. Now if we want to calculate packing density, that will be 4 into 4 third pi r cube, right? By a cube. Now we need to have the relation of A with R. How you can get it? Now the atom is present in the face. So this if you just draw this plane, the above plane I'm talking of, just draw it. So this is a square with A, and there is one atom, then is one atom, and there is one. So any diagonal of any square having the side A, the diagonal will be root 2A. So root 2A will be equals to, this is 2R, this will be R, and this will be R. This equals 4R. So what will be A? 4 by root 2 R, and just put this here. And if you calculate it, it will come 0.74. So that means 74%. Right? So in case of BCC, that is 68%, and in case of FCC, it is 75%. So from this, you can know like the FCC is much more like there is less space left. That means this is much more closely packed, right? So this will be much more closely packed. So that means if you compare with BCC and FCC, then obviously FCC will be more closely packed. So this was just the extension I want to discuss. Now come to the next question. What is it? Which among the following surface has the lowest packing density? Now we talked about this is packing density of the whole lattice, that is in the 3D. Now we are talking about packing density of the surface. That means that's a plane, and the packing density of a plane is defined by number of atoms in a unit cell divided by area of the unit cell, right? Number of atoms, again like what we have said in case of BCC also, the number of atoms present in the unit cell, and then area of the unit cell. Now, as have discussed, you can see it in lecture number 3. Like he has given all the example like FCC 100 plane, FCC 110 plane, FCC 111 plane. For everything, like these are the 3D arrangement of the plane. Okay. Now, if you want to like calculate the packing density. Before calculating, you just see the picture. Like just by looking at the picture, you can know that FCC 111 is having highest number of atoms. Like this is very very closely packed, and BCC 111 this is very loosely packed. Like there are so much space in the plane, but in FCC the very less space is actually left. So if you don't do any math, you can directly say like which is having highest packing density, that is FCC 111, which is having lowest packing density, that is BCC 111. Right. So this by this also you can answer this. So this will be BCC 111. Now, like the what is the analogy behind this? Like like in all the cases, if you think like a single atom, like what the examples Sarah has given, that is copper 0.25 nanometer, that is the lattice parameter. Now if you think of like copper that is actually having actually forming BCC and FCC both, which is not the case obviously, then it will not have same lattice parameter. But if like copper is actually making both FCC and BCC, and you are taking one plane, so the packing density parameter will come like 0.31, 0.22. If you calculate that, then it will come like this. And from the calculation also, you can see the BCC 11 is having the lowest. So that means BCC will have the lowest packing density, right? So come to the next question. I'll discuss about this planar packing fraction as well, but after discussing all the question, if time is left. So let me go to the next question. So what is the question? Which of the following are two-fold and six-fold symmetry? So you need to go one by one, like whatever is given, you need to go one by one. Let's say first one is BCC 100. So this is BCC 100, and this is the unit cell. So you can clearly see this is a square. Square means this will have a fourfold axis of symmetry. What is fourfold axis of symmetry? Like think about axis which is actually coming upward. So like coming upward and going through the plane. So now through this axis, if you rotate it 90 degree, so then this atom will, if this is one, this is two, this is three, let's say this is four. So one will come in the place of two, two will come in the place of four, four will come in the place of three, and similarly this. But as all the atoms are same, that means there will be no change in the symmetry of this. So that means this is actually having a fourfold axis of symmetry. That means if you rotate it 90 degree, then also the symmetry of the crystal will be same. So this BCC 100 is actually having fourfold, not the twofold. Like now go to the, so that means this is not the case. Now go to BCC 110. What is BCC 110? This is actually having a rectangular kind of shape. So rectangle means this, if this is A and this is B, these are not same. But in case this is, if this is A and this is B, this is A and A is equals B. That's why it is square. But in case of rectangle, this is not same. So now if you use a like fourfold again, so then just try to visualize it like this. Okay. Sorry for, I'm just writing, drawing it. Let's say this is a rectangle, and you are actually having a C4 fourfold axis of symmetry. That means you are trying to rotate it 90 degree. Now let's say this is A, B, C, and D. So if you rotate it in this direction 90 degree, what will happen? This will look like this, where A will be here, B will be here, C will be here, and D will be here. Clearly, now this and these are not same because actually because the this parameter is actually changed. If it was A, now it is B. These are not same. So it is clearly not having any fourfold. But if you rotate it 180 degree, that means if it is having C2 symmetry or like the two-fold axis of symmetry, then after 180 degree rotation, you will get again same kind of structure. Just A will come to this, B will come to this, C will come to this, and D. But these two are having again similar kind of parameter. That means this is actually having twofold, right? No, so that means this option first part is right. Now I want a six-fold symmetry. So if you go for FCC 110, this is again a rectangle kind of thing. So that will obviously have twofold, not the six-fold. So this option is not right. Now come to the BCC 111. BCC 111, does it have? BCC 111 will have again like a six-fold, but this one we already proved it is having twofold. That means this is also PCC 110. So this will also have twofold. Now come to the FCC 111. Does it have a sixfold? Yes. This is actually hexagonally. Like if you think about any point, you can clearly see a hexagon. How? Right? This is a hexagon. So this point, this will have a sixfold axis of symmetry. So that means this will be your answer. BCC 110 is having twofold and FCC 111 is having sixfold. Yes, in the order. Get it? Last one, yes, yes. Yeah. Because BCC 110 is having twofold and FCC 11 actually FCC 111 is having sixfold axis of symmetry. Right? Because it's a hexagon. Now, yes, yes. Yeah, tell me. Yeah, BCC 111 will also have a six-fold symmetry. Just try to visualize it like this, right? So now I already talked in the first slide about surface reconstruction. So I said in surface, any surface, in the surface it will have low density and low coordination number, and due to which the surface energy will be high, and it will try to minimize the surface energy by going a reconstruction. And this surface reconstruction is actually true for every surface you can think of, because this in every like for any surface there will be low density and a low coordination number in the surface. So like irrespective of any surface you think, it will go surface reconstruction. So it will be all of the above, right? Because this is also surface, this is also a surface, this is also a surface, and it will go surface reconstruction. And you can find like the analogy in the lecture number 5. So I have also written in order to stabilize, that is minimizing the surface energy, any surface is going to reconstruct it. So if somebody is asking a question, which surface will go reconstruction? Everyone, right? The extent of reconstruction, like the extent of minimizing energy, will be different. Like if a surface is actually very less packing density, then it will try to like that means it is having much lesser coordination number, so that means it will go more reconstruction. But a certain amount of reconstruction is always there. So all of the above, the answer will be correct, right? Now, I was talking about reactivity of the surface. This is the question. Which among the following is the least reactive surface? So, reactivity is actually in this order, right? So, the surface which will have higher packing density will be less reactive. The surface which will have lesser reactivity will be much more reactive, right? So just see FCC 111, BCC 111, BCC 001, FCC 110. So here in the lecture, Sir has already given the surface, packing density parameter. This is 0.31, 0.22, 0.35, 0.15, right, like that. So which one is having the lowest packing density? That is clearly BCC 111. And which one is having highest packing density? That is FCC 111. So among these, this one will be least reactive because the packing density is the highest, and BCC11 will be the highest reactive. Obviously, highest and lowest is depending upon the options are available, right? So there will be some surface which is more reactive than BCC111. That is also discussed in the lecture. So there are the high index surface, but FCC11 is always the least reactive surface because it is having the highest packing density. So what will be the answer? This will be FCC111, right? You already know that this question is actually discussed in the lecture itself, right? Let me just check if somebody is actually joining right now. Let me go. Okay. Now, let me go to the next question. So, it is written, what is the symmetry group of a hexagonal lattice? Right. So, just try to draw a hexagonal. And here, P means primitive. What is primitive? Where in a unit cell only one atom is present. That means, sorry, this is one. What is primitive? That is only one atom is present in this unit cell. And that means that all the atoms, in case of cubic, will be corner share. In case of 2D plane also, that will be like if all the atoms are only corner share, that time these are called as primitive. Now, C means that is center. Like if something is in the center, some atom is present in the center of the unit cell. That time it is denoted by C. So in all the case, if like normal hexagon cell looks like this, hexagonal lattice looks like this. So there is no atom in the atom present in the center. If you can recall the graphite structure as well, so that means it will obviously be P. This is primitive, right? Now, what does this 2 and 6 means? This means the symmetry. Like this is the 2 means two-fold axis of symmetry. 6 means six-fold axis of symmetry. 4 means four-fold axis of symmetry. So in case of hexagon, we already see. But in case of a hexagon, that six-fold axis of symmetry is present, right? So now whenever we try to discuss about hexagon, that means it will be 6. So only this option is correct. Now also what is mm? Mm is nothing but the mirror present. So there is this mirror is present. Also this mirror is present. Two kind of unique mirror is present. One is through the atom and one is between the atom. So this is one end and this is one end. So someone you may tell like there are other mirrors also present like this, right? But just think these two, the green two, are same like this. These are going through the atom. Just I'm just choosing the different atoms. But these mirror one and mirror two are different because this mirror two is going through atom and mirror one is going through the space. So two unique kind of mirror is present. That's why it is mm. So what will be the answer? It's a primitive cell. So P will be correct. So this is not the option. Now this is a hexagonal lattice. That means a six-fold present is there. So that means P6 and mm already discussed. So this will be my answer. P6 and this all the lattice here. This lattice are in the 2D, right? Because there is only one plane. That's why there's only like five options are there. In case of 3D, I already discussed how many options. That is a 14, right? This question. 14 kind of like total 7 system, and depending upon the atom position, we can get 14 varieties. In case of this is the case for 3D, and the question they have asked that is for 2D, right? So somebody join and okay. Okay. So we have come to the last question. This is a very, very important question and very interesting as well. So, which statement is not true for a graphite surface? First of all, let me tell, graphite surface is having a hexagonal lattice structure, hexagonal, right? So if it is a, so that means this is also like we all know graphite structure. So this is a hexagonal graphite lattice. That is true, and they have asked which statement is not true. So this one is true clearly. It has two different type of atoms. Like you can think this is very like how can it have two different type of atoms? But what is graphite? Graphite will have obviously like carbon and hydrogen, right? So that means two type of atoms are present. That is also true. And STM topograph. STM is scanning tunneling micrograph. So I will discuss it in like upcoming lectures. How like what is the principle of STM and everything. But STM basically talk about like a surface. Like if a surface looks like this, so STM topograph will give this like topology. How it is like here there's up, there's down. So how the surface looks, STM topograph will show that. So if you think like hexagon in a very close manner, like an infinite number of hexagons are arranged like this will look like a honeycomb. Obviously, like honeycomb structure you have already seen, and in the lecture also the actual honeycomb structure how it looks like from like actual steam structure how it looks like for a hexagon is given there as well. You can go find it in lecture number 5. So it is also true. It is having honeycomb type of pattern. Now come to the basal plane, and that is given that is a Miller indices, right? Indices. So we need to know Miller. What is Miller indices? We already know. Sorry, we already know in case of a cubic how we define Miller indices. Let me just show you at first in case of a cubic. So what is Miller indices? Miller indices is nothing but to assign a plane, right? You can assign any plane using Miller indices, and it is normally written as H, K, and L. So what does it mean? H means 1 by intercept at x-axis. I'm not writing the axis. K means 1 by intercept of y, and L means 1 by intercept of z. Okay. So if it is my x-axis, if it is my y-axis, and it is my z-axis, so the plane, whatever plane you are talking about, in which position it is cutting the axes. Depending upon that, Miller indices is actually defined. So, like let's say I am trying to talk about this plane, right? I'm trying to talk about this plane. What will be the Miller indices? So this is my x. So this plane is actually never cutting the x-axis. That means this is parallel to x-axis. So that if we try to find the intercepts of x, y, and z. So what will like if it is parallel? That means it is never cutting. That means the intercept will be infinite. And y, like this is a unit cell, so it is cutting y at 1, intercept is 1. And also for z, it is never cutting z, so it is again parallel to z as well. So that means the intercept will be infinite. So to get Miller indices, you need to just take the reciprocal, right? So what will be Miller indices? 0, 1, 1, right? So this plane is 0, 1, 1. Normally, no comma has been put there to show Miller indices. But if just a point, if the number some like in case of plane, the number actually cross one digit. Let's say the if the plane is like 0, 12, and 1, that time normally people put comma. Up to one digit, normally no comma is there. It's only space. But if it is a two-digit plane, then only in case of Miller indices we put comma, right? So let me take one more example. Let me put one slide in this place. We can like take some. Let's say it is given to show 0 to 0 plane. That plane is having 0 to 0 Miller indices, right? And you need to show. So it is just the opposite question of the first one, what we have discussed. So at first we just draw the cube, right? And defining the axes is very important because depending upon the axis, we will get the planes. So this is my x and z. So if such kind of question is there, 0 to 0 plane, what we will try to get? The value of intercept. So what will be intercept value? Just nothing but taking the reciprocal of the Miller indices, because taking the reciprocal of intercept will give you Miller indices. So taking the reciprocal of Miller indices will give you intercept. So what it will be? 1 by 0, 1 by 2, 1 by 0, right? So this will be infinite, this will be half obviously, and this will be infinite again. So that means the plane will be cutting y-axis in half position, and other with respect to other two axis it will be parallel. So there is, it will be parallel with respect to this and this. So now if we let me just change the color. So if we try to draw, so if it is one total, that means this is half. Sorry. So that means the plane will be like, sorry, my drawing is not great. So this, right? So this will be 0 to 0. So you need to go in reverse manner. So now in this picture, if I want to show 1 1 1 plane, if I want to show 1 1 1 plane, this is very simple because all the intercepts will be nothing but 1 by 1, 1 by 1, nothing but 1, right? All the intercepts are 1 practically. So it will cut x-axis at one point, y-axis at this point, and z-axis is this in this point. So this will be 1 1 1 plane, right? This will be my 1 1 1 plane, right? No problem with this. So like that, in case of hexagonal, you can clearly see you cannot define any plane with just taking three axes, because there is some like there is two planes that are connected in z direction. So that's why the normal practice in case of hexagonal lattice is to take like four coordinate system like h, k, I, and l to define a Miller indices. Yes, yes, yeah, yeah. I'm telling that in case of cube, you can define it by h, k, and l, only three axes, and that's why three indices. But in case of hexagon, we need one more because the two, like in the plane itself, there is like xy, like there is three kind of coordinate is possible, and then also two planes are connected. So you can, like in case of the practices for hexagonal lattice, we use four indices, Miller Brave indices. So and that is defined like h, k, I, and l. And this is like just the plane is defined by a1, a2, and a3, and whatever intercept it is making with a1 is called as H, which will correspond to H, A2 will correspond to K, A3 will correspond to I, sorry, I, right? And the interplanar, like the Z direction, it is called as L. So in any plane in hexagon is actually defined by these four coordinate. And also there is a special kind of relation, that is I, this I is always is equals to minus all over h plus k. So if you add h plus k, then I will be automatically defined, that will be minus h plus k, right? So let us designate this plane which I have already drawn, right? So first thing, this is my, so this three, right? Sorry, sorry. This is the defining system A1, sorry, sorry, A2 and A3, not this, like this. So this is the defining system. So this is my A1, this is my A2, and this is my A3, and this is the Z direction, right? So this plane is cutting A1 at one position and A2 at one position as well. But A3 is in this direction. This is the positive direction of A3. But this is cutting A3 at half position in the negative, right? Because this is the positive direction of A3 and this is the negative direction of A3. And the plane is cutting A3 at the middle of that. So that means if we take the intercept, right, of A1, A2, A3, and Z, I think. So A1 is intercept at 1, A2 is at 1, this is at minus half, and Z is actually parallel to Z. This plane is never cutting the Z axis, right? This is parallel to Z axis. So that means the intercept is infinity. So what will be the Miller indices? Just the reciprocal, right? So you'll get 1, 1, minus 2, and 0. Normally, in case of in case of any lattice, the negative is denoted by bar. So the Miller indices of this plane is, if you can write this as well, minus 2, but the normal practice is uh, assigning negative to a bar. So the plane is 1, 1, 2 bar 0. So now come to the question. Sorry, now come to the question. So they have seen, like they have written, its basal plane is 0, 1, 0, 1. So what is the basal plane? These planes. This plane of these planes are called as basal plane. So this plane normally is basal plane. Like now, if we try to define the Miller indices for this basal plane, what it will be? So this is my A1, this is my A2. Let me change the color. Sorry. So this is my A1, this is my A2, and this is my A3, right? A1, A2, and A3. And this plane is never cutting A1, A2, and A3. So there is no intercept. This plane is parallel to all A2, A1, and A3. But this plane is actually cutting, intersecting the Z axis at one position, right? So what will be the Miller indices of this? So just write down the intercepts. So A1, A2, A3, and Z, right? So this is infinity, 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 and 1, right? 1. So if you take the intercept, that will be 0, 0, 0, and 1. So this is the Miller indices for the basal plane 0, 0, 0, 1. What it is written 0, 1, 0, 1. So clearly this is not the basal plane for a graphite surface. So this statement is not correct. So this is actually your answer. Sorry, this is actually his answer. All these are true except this. So this is your answer, right? So I have discussed all the questions. Let me see just if there is time left. So I'll try to discuss one thing, one very short thing, and that is related to the packing density. So we have discussed the packing density for a lattice, right? Packing density of lattice. How what it is? The packing density of lattice is the volume of atoms present in the unit cell divided by volume of the total unit cell. And there is also one similar kind of thing defined for a plane, like the surface. We are talking about surface, right? So there is the surface is actually there is also a parameter. What is that? That is called as planar packing fraction. What it is? What is planar packing fraction? Packing fraction is uh, defined as the number of atom, so like present in the plane or in the surface into the area of each atom divided by the total area of the plane. So let me write it first. So ppf This is a short form. Planar packing fraction. This is only for a surface or plane. So what it is? I'm telling area of atoms on the plane or surface divided by area of the plane. So if we think about any plane like this is a surface. Let's say there is one atom. So total area, if this is A and this is square, then total area is obviously A square. And how much area is occupied by these atoms? This is giving you the planar packing fraction. So packing density is number of atoms just divided by the area, and planar packing fraction is area of atoms on the plane divided by the area of the plane. That is not discussed. I just uh, thought of sharing this with you. This is a common parameter that is actually discussed in case of a surface or in case of a plane. So now let's say we will just do this for one plane. Let's say this is for FCC 111, right? So at first, let me draw the FCC crystal. So FCC, that means in every corner there is one, right? And then in each face there is one atom, like that. So now think about the 111 plane. What it will be? I've already discussed the Miller indices. It will be nothing but this plane, right? So now if we cut it out and just see this plane from the top view, right? This is the plane, I'm seeing it from this top view. So how it will look like? It will look like basically a triangle, because this is a triangle with each of the corner is having one atom. Also, this line is going through this surface, so that means there will be half of an atom present. There will also be a present one atom. So these are the atoms I'm talking about. This one atom, there is also one atom, this one and this atom. Okay, so this will be my the surface I'm talking about. So if we think the area of the atoms on the plane, so this much area is given by this atom, this much area, this much area, this much area, this much area, and this much area, obviously, right? These areas are contributing in the plane. So this total area divided by the area of the whole plane. So how it will be? Am I audible? Hello, hello. Yes, yes. So if you don't understand, just ask me. So this is the plane. This is FCC 111 plane, and this. So what are the number of atoms present in this plane? So just think this is a triangle. So that means this atom will be shared by how much triangles in the plane I'm talking. So there can be one like this, one more triangle, one more triangle, right? One, two, three. So obviously this will be a hexagon, right? Like one, two, three, four, five, six. So each atom in the corner can be shared by six similar kind of triangle. So and you have three corner atom present in this plane. So three atoms and shared by six, right? Plus these atoms will be shared only by this triangle and this triangle. That means each one of the atoms present in the middle of the plane, middle of the surface of the plane, is shared by two triangle. That means half into there are one, two, and three total atom. Half into three, right? Is it visible? Whatever I'm written, so I'm written in number of atoms present, right? 3 into 1 by 6 plus 3 into half, right? You understood? I'm talking about just the plane, right? That's why I'm not taking anything about the plane. So this atom is shared by 6 triangle, and these atoms are shared by 2 triangles. That's why I have taken half and 1 by 6. So if you calculate this is half and this is 3 by 2. That means total 4 by 2. That means total 2 atoms are present. Right? Right? Now, what we need to calculate, that is the area of this plane. So the area of just this plane I'm talking. Area of this plane. So this is a triangle. What is the area of a triangle? If this is height and this is the base, so normally area of a triangle is area of a triangle is normally written as half base into height, right? Half base into height is the area. Now we know, we know what you know. This is the base. So this means r plus 2r plus r. That means this is total 4r. Will be equals to, this is the diagonal of this surface. This will be equals to root 2a, right? But you just think about only r. This is obviously a relation. So that means this base, this is r, this is 2r, and this is r. So this base, total base, is actually having 4r distance. So half of it is 2r, right? Now I need to find out this h. We all know about the Pythagoras theorem. What it tells, that square hypotenuse square is equals base into heights. So that means if we write h square plus b square is equals this, and this is again what, r plus 2r plus r means 4r, right? This distance is again 4r, right? So that means this will be 4r square. And what we said, b is nothing but 2r square. Sorry, 2r whole square, and this is 4r whole square, and this is 8. So what will be your h square? Nothing but 4r square minus 2r square. That means it will be 16 minus 4. That means 12 r square. That means h will be equals root 12 4. Right? Get it? So now we need to find out the area. What is the area of the plane, that is triangle? Half into b. B means nothing but half into b means base total. Don't confuse this with this one. This is the whole fora. This is the base of the triangle, and the height is root 12 r. Right? Get it? This is the base of the triangle, that is 4r, into height we have found out, that is root 12 r. And now we need to find out the PTF. What it is? It is, we found that 2 is a total number. 2, and area of any atom, any circular atom, is pi r square divided by half 4r into root 12 r. This r is going to cancel with r square, right? This is 2, it will come up. So 2 and 4 will cut. So we'll get pi by root 12. Right? This is the planar packing fraction of FCC 111. You can try FCC 110 or BCC 111 similarly, uh, in this manner. You just need to find out the area, you need to find out how many number of atoms are present, and then what, just the area of the atoms divided by area of the plane. That is called planar packing fraction, and that is also that also the, like, if the planar packing fraction is high, that time it will be least reactive. If the planar packing fraction is very less, in case of BCC 111, you can find out all, if you find all the packing fraction of FCC 110, 100, and 111, and BCC 110, 100, and 111. You just try it in home, and you can see there will be the least packing fraction, planar packing fraction for the BCC, and that is also. So that's why I tried to. So in this lecture, I have discussed all the assignments. I think you have you got the answers clearly. So okay, thank you for your attention. So I'll assignment to in the next week, same time. Yeah, but actually, I am bound to do this in the Saturday only, because like at first you need to try by yourself. Then only I'll do like so. It is like that only. Yeah. And actually, this this is not my subject as well. So I have to prepare and then actually deliver, right? Because I'm doing research in different subjects. So this subject is very new to that. This color class is actually BSc level. That's why it is okay. But the upcoming lectures also are a bit difficult. So I have to prepare. I don't think I can like discuss it. Yeah, I can talk to them. I don't know them personally, but you can actually mail or write in the discussion forum as well, right? Yeah. So thank you for your attention, right? So I'll stop here. Yeah. Yeah. Have a good day. Bye.